When you flip a switch, it is tempting to imagine electricity flowing through the walls like water through a pipe, a continuous, one-way river of energy rushing from a power plant straight into your device. But the grid does not operate on a one-way street. The power running the modern world is actually a rapid back-and-forth oscillation. The electrons vibrate in place, pushing and pulling on each other rather than flowing in a single stream. This oscillating model is known as alternating current. It defeated direct current in the late 19th century to become the global standard for power distribution. To understand exactly how the grid functions, we have to look past the steel pylons and copper wires. We have to examine the strict mathematical geometry of the power itself. Alternating current operates as a precise mathematical function that physically dictates the engineering requirements of global infrastructure. To see how this infrastructure works, we first need to define what this oscillation looks like in formal physics. These foundational notes lay out the rule. An alternating current is defined as a current whose magnitude changes continuously with time and whose direction reverses periodically with time. The power level is never static, changing every millisecond, and the flow of electrons must flip backwards. These two constraints, continuous change in pressure and periodic reversal in direction, are intrinsically linked, creating a highly predictable system. Physicists and engineers use a specific tool called a waveform to visualize this exact mathematical behavior over time. True alternating current is defined by this unbroken rule of constant mathematical change, which is what separates a usable power grid from chaotic electrical noise. This written definition translates directly into a mathematical formula. These two core equations govern the flow of the electrons and the pressure pushing them. Capital I and V represent instantaneous current and voltage at any millisecond, marked by lowercase t. Im and Vm stand for the absolute maximum peak amplitudes. This peak amplitude is the absolute physical limit of the wave's power. The current hits this ceiling right before it begins its inevitable decline. The mathematical engine driving this rise and fall is the sine function. It forces the current to smoothly curve rather than snap abruptly between values. Inside that sine function is a symbol called angular frequency, represented by the Greek letter omega. Angular frequency dictates the speed at which current completes its cycle and reverses direction, typically 50 or 60 times a second, depending on the regional grid. Finally, time, t, acts as the independent variable. As time marches forward, the equation continuously produces new values for current and voltage. These specific variables translate the abstract physics concepts of continuous change and periodic reversal into a strict calculable model. We can see how this mathematical model behaves in physical reality by plotting these formulas on a graph. These side-by-side charts graph both the current, I, and the voltage, V, over time. Notice the dashed lines at the top matching our maximum peak amplitudes, Im and Vm, mapping exactly to the physical crusts. A full cycle starts with electrical pressure at 0. The line arcs smoothly upward until it hits that maximum positive peak. Obeying the rule that magnitude must change continuously, the pressure immediately curves back down, falling all the way to the 0 line. The curve then plunges downward until it hits the exact opposite limits, negative Im and negative Vm. Once the current hits that absolute negative peak, it climbs out of the trough and rises to the 0 line once again. Hitting that 0 line marks the completion of exactly one full period. The electrons are back where they started, ready to repeat the sequence. This dip below the axis is not negative energy. It is the physical manifestation of the current changing directions, flowing fully in reverse. These graphs visually prove the foundational definition. The power grid operates on a perfect, unbroken cycle of rising, falling, and reversing. The obvious engineering question is why we rely on this oscillating waveform to power our homes instead of a steady, flat stream. The answer lies in the primary systemic advantage of alternating current. As these notes observe, AC voltage can be easily converted to other voltages by using a transformer. This conversion is handled by massive industrial transformers located all along the grid. A transformer has one rigid physics requirement to function. It needs a constantly fluctuating magnetic field to operate. This is exactly what the sine wave provides. As the magnitude of the alternating current continuously rises and falls, it generates a magnetic field that repeatedly swells and collapses around a coil of wire. This pulsing magnetic field sweeps across an adjacent secondary coil of wire. The motion of the field physically induces a brand new voltage in the second wire, allowing engineers to scale the peak voltage dramatically up or down depending on the number of coils. Direct current functions differently. A flat, continuous flow of DC electrons creates a completely static magnetic field. Because a static field does not move, it cannot induce voltage in an adjacent wire. Direct current cannot be stepped up or down through passive induction. Without transformers, a power grid is trapped. Whatever voltage leaves the generator is the exact same voltage that must travel to the end user. The geometric curve of the sine wave provides the physical conditions necessary to manipulate electrical pressure. The ability to manipulate voltage solves the single greatest barrier to building a wide-scale power grid: geographical distance. The final major advantage noted in the source text confirms that electrical energy in AC form can be easily transmitted over long distances without much loss. Pushing large amounts of raw current through a wire creates immense friction. Without intervention, significant amounts of energy dissipate as heat before reaching a city. These immense, high-voltage transmission towers exist specifically to bypass that friction. By routing power through a transformer and stepping the voltage up to extreme levels, the actual current flowing through the line drops proportionally. Pushing extreme voltage with incredibly low current allows power to travel hundreds of miles through regional cables with minimal heat loss. Once the transmission lines reach a destination, local substations simply reverse the process. They use transformers to step the voltage back down to the lower, safer levels required to run household appliances. The continuous change and predictable reversal of the AC sine wave establish the mathematical and physical parameters that allow the global electrical grid to function.